So thanks everybody who made it to part 2. I appreciate you coming, and also I understand that this A, this is you've been listening to me for an hour and a half, or some of you, and B, that you're already tired. So if you want to doze off and be on your phone and whatever, like just don't snore and be good. Don't worry about it. Okay. So what the second part is about? Like the slides are still there. So it's JFDY 2025 part 2. Okay. What are we going to talk about? Unfortunately, this is just a kitchen sink of a talk. Like I need to explain a bunch of things. So we're going to start with some big unsolved issues. We're going to talk about customization. Then we're going to talk about tail handling. And tail handling is a fairly big topic. I believe that's one of the most important subjects in SIMD library design. Then we're going to talk about ranges. And finally, when everybody's completely tired, I'm going to address all the controversies so nobody can defend themselves. Let's start with some big unsolved issues. Dynamic register sizes. So I have been saying, like this is the thing, like wide size. Right? I'm saying this is 32 bytes on my machine, and I'm going to rely on it everywhere at compile time. Well, newer architectures like latest ARM and RISC-V, in their specification, they don't tell you what the register size is. They say our register size is between 16 bytes, let's say for ARM, and 2 kilobytes. And you're like, how to program that? That's so weird. It's even, but on your machine, it should be a specific one. Like, so on ARM, it mostly will be 16 bytes, but it theoretically can support like a server that would prefer a really big one, right? And it exists, like servers that have 64-byte registers. And then it's more than that. I'm saying, okay, your machine knows your register size. And it's not necessarily true, because on ARM again, there's a thing called streaming extensions. Now, to the best of my knowledge, it's not really done that way anywhere. But the idea is that you have 2 sets of registers and you can switch. You can say, okay, now I'm going to use a different set of registers that's going to be, for example, different size. So you can switch from 16-byte registers to 32-byte registers. There's a little bit overhead to switch, but then you get faster. So the standard doesn't support this because this is very new stuff, and it makes sense for the standard to not support very new stuff. However, why don't we in Eve support it? And a fundamental problem is that like something like this. So this is the type for ARM intrinsics for integers. So this is, says SV int u32, so unsigned integers, and you don't know how many. Because you don't know how many, you cannot take a size of it. It's a weird type. It's something that's known as sizeless types. It's an extension. And if you can't take its size from it, you cannot put it in a struct. Like there used to be, the only library that supports this at the moment is Google Highway. So in Google Highway, they said, we really want it. And because they say we really want it, they sacrificed as much as was needed to get this to work. Like, for example, to the best of my knowledge, you cannot do zip in Google Highway because they wanted to support this specific case. There was an extension. There was an extension called sizeless struct. So you could take, you could create the sizeless struct, and then I could put registers into it. And I can, if it has a sizeless struct, now I can attach meta information. What I need is to be able to attach some meta information to it. This is my type. This is how many elements are active. This is whatever. Unfortunately, this extension was removed. So Richard Sandiford was responsible for extension, and then I believe he removed it as well. And there are only some specific, very fixed structs that shipped into ARM APIs that now exist. You cannot write custom ones. If we had that, we could do it. So how do we propose it to handle this in Eve? How do we suggest you handle different register sizes? We suggest you compile multiple versions. So you take the function and compile multiple versions. Unfortunately, that's also tricky in C++. The best case, what we propose is DLLs. But, you know, so what now? You are needing to change how you ship your code. You need to now, with your binary, ship DLLs with kernels and you load the appropriate ones. That's very annoying to do. We can try to do one binary in if we don't have it now. In Google Highways, they have something. The problem with one binary compiling multiple versions is ODR. Right? You start with a function, you compile multiple versions of the same function, you break one definition rule. Certain things you can try to do with like inline namespaces, but it's tricky, not impossible. And I absolutely do not know how any of that works with modules. So modules kind of implies the same set of compiler flags. This is, you need different compiler flags for the same files or whatever. Basically, we don't know, we don't have an answer. If the standard could help, that would be great. Customization. You would like to tune some algorithms. We already saw this a little bit, but use cases can slightly differ. And you want to write experiments. Like, for example, you want to unroll differently. Like, we saw the sparse dense copy, like that may be relevant. But even if I know that something is a faster version of it, you would not trust me. Like, as a performance engineer, you want to try everything. And so basically, we believe that if we give you as much control as we possibly can, and then like everything is also an onion, so if you really need it, you just can unpack a layer and go there. On a similar topic, you want to be able to use intrinsics directly. So you want to be able to combine whatever if or standard SIMD with the native instruction. So let's, there's an example. There's an instruction, JF2P8 affine QB. Right? We call it Jeff. So it computes an affine transformation in the Galois field 2 to the power of 8. Does anybody know what that is? No, me neither. However, there's this person, Harald Uproot, who uses the whatever affine transformation of something to do bytes histogramming, like counting which bytes. I don't know. I didn't figure it out in detail. It was very cool. But you want to be able to, there's no way this is going to be shipping with the SIMD library. You need to be able to extend the SIMD library with your custom stuff. So let's look how this is done in if. First of all, I'm calling like a transform to, right? And inside, so in standard, you have just transform, that just always accepts an output. In if, we have an in-place version as well. I'm not sure now that it's worth it. It helps with the tails a little bit, but that's the extent of what it does. And inside this transform to, I have a predicate. So with zip, there's the input. There's the input range 1, input range 2, output range for the output. So I'm gonna zip 2 input ranges to produce your new range. The value type of the zipped range is going to be wide of tuple, as we saw in the first part. I decompose that for x and y, and then I just apply the intrinsic. So in if, all the whites are implicitly convertible to the appropriate intrinsic type. The standard recommends this. So the standard SIMD is recommended to be implicitly convertible to the appropriate available intrinsic representations, or it is bit castable. So you can trivially, if it's not implemented, you can bit cast. They unfortunately cannot mandate it because they cannot talk about the types that are outside of standard. Let's look at some tuning as well. So the tuning in if is done with the square bracket syntax. So all the functions you just pass extra parameters in like square brackets. So here I say don't unroll. Basically means that if will not unroll. Compiler will anyways, but we didn't. I say that aligning here is not beneficial because the instruction is complicated, I decided. Yeah, frequency scaling we're not gonna touch. Does this kind of look okay?
The only thing I don't understand is that so this only works if Eve wide is an AVX 512, like.
Yeah, you have to, you can only, so comment was, this only works if this is in a platform where the instruction is available, and yes.
Well, no, and the Eve has to be choosing to use ZMM registers instead of like YMM.
Yes.
So like, where in the code is that like expressed?
No, that's just how Eve works.
Okay.
So the comment was that this mandates a certain representation from the Eve registers. Right, and that's absolutely true. And that's going to be absolutely true for standard SIMD. How they're represented internally is part of the interface. Like there is no escaping that. Okay. A similar form of customization is what we call domain restrictions. So let's say this is SIN, right? And the standard ships a SIN as well. And this is our implementation of SIN. It's about whatever 800 instructions. You know. However, the way it works, most of it has to deal with reducing the angle within a certain range. And so actually, if you can tell if, oh, okay, this is just within -pi/4 to pi/4 using this command, quarter circle. And then when it compiles, it will be better. Yes, thank you very much. So it's 30-something instructions. You can write a check that will say, okay, if all of my angles are between certain things, but that's still a check for certain instructions that can be substantial. Standard doesn't have any mechanism to do it. You can try to do built-in assume, saying, okay, assume that my float is within the appropriate range. Then your compiler has to know what SIN is, which can be tricky. Like, okay, for SIN, it totally makes sense, but what about some other functions? So we have a lot of customizations like this. Next topic is tail handling. Like I'm saying, it's a bit of a kitchen sink. Any questions so far?
So Eve quarter circle means I'm guaranteeing that each element of X is in the quarter circle when
yes.
interpreted as an angle.
Yeah, that's what it means. It guarantees that you guarantee that this assumes that the angle is within the range. Let's talk about tail handling. So tail handling is very informative. It informs everything else about your library, about your ranges library. Let's start with the simplest one, scalar one. So this is something like this. You have an array up to the first, let's say, aligned, if we do aligning stuff, up to the first aligned address, we will go in scalar. Then we start doing SIMD. Then we do scalar cleanup at the end. So on the plus side, it's very simple. Like it's very simple to explain. It's fairly simple to write. Another one is that all the values that you get, what indicates is no garbage, all the values that you get inside your predicate, you get exactly once, and you get them only the values present in the input array. That's not always the case. Right. Minuses can be slow. So this, like if you need to process, let's say 30 chars before you start doing vectorizations, that's not great. But the biggest one is predicates. So because now you have all of your callbacks have to accept both scalar code and SIMD code, right? You need to do operations on, like, let's say if it's just chars on the char, on a wide of char. Every SIMD library out there tries to make this more seamless, including standard SIMD. So it tries to pretend that you're writing scalar code, but this is still annoys people, especially when they want to do intrinsics. So now let's say if you want to use that Jeff function, you need to figure out what's the scalar version of the Jeff function. Right? It's not nice user experience. People actually complain about this. The next one, this is the one we use in Eve. Same thing, you have an array, and we have, on top of just having regular load, we have load with ignore. So you can, you say, okay, load from here, and don't load the elements here and the elements here, right? So like this. So in the beginning, I'm saying I'm going to go to the previous address previous aligned address, and I'm saying load me this register, and everything in here is don't load, right? It's okay if it's some garbage, but don't load it. Same as the end. In the standard, they have standard SIMD partial load, This is exactly this. So you can load from a position, but you don't load the entire register. You load only within subrange. And they also have a load with a SIMD mask, where you use a SIMD mask to specify which elements you don't want to load. This is with this you can do everything, but unfortunately it requires an instruction. So if you have an instruction, this is great. If you don't have an instruction, this is slow and unusable. Pluses, one argument type. So the biggest reason why we did this is because we really wanted the predicates and all the callbacks to accept just the SIMD register of just one size. We use the aligned tricks that we talk about under the hood here. So when you do the load with ignore, you say, oh, okay, I want to load from but you give me an aligned address, I will just convert it into just a regular load, and you will never have to know about it. That requires certain restrictions on the load function itself. The load function has to specify that you have to load from a valid pointer, things like that, but well, we do it. I'm not sure that's a good idea for the standard. We do. Minuses. If you do a store, or if you do an unaligned load, so when I don't know that the pointer is aligned, it's not very fast. It's not the end of the world, but it's not very fast. This ignores things. And you have the garbage in your predicates. So I'm just going to mention this for a second. Think about it. If you have a garbage in your predicate, it means that you can never enforce a precondition. Like every precondition, like you divide by 0, you have the division by 0 has to succeed on 0 in some meaningful, like it has to produce a value. It cannot say don't divide by 0 because we loaded the values, we don't know what's in there. Like we will talk more about this, but if you ever want to do while loops that don't have the right boundary, you don't know where, like things like strlen, where you don't know where you stop, you have to eat it. There is no escaping. You will have to accept that sometimes you load a value that is arbitrary. The final one is overlapping tails. Remember we had this picture. So we had two registers that were overlapping and you had the dispatch. On the surface, this seems like it's just strictly worse than scalar in terms of the interfaces, because now you don't only support scalar and SIMD, you have to support everything in between, like you have all the cycles. However, what you can do is you can take a small register and you can extend it to a bigger register. Like if the cheapest version of extending is to eat garbage here. So to say this is arbitrary values, we don't know what's in there. Right? Then if that's your conditions, this operation is very cheap. You can also, if you feel, how many people feel that out of the people who don't fall asleep yet, that the garbage values are something they're willing to live with? Okay. What if it was zeros? What if I guarantee you that the value that you load is a real value from the array or a 0? What if I give you, it's a value from the array, but the value can repeat? Because what I can do here is I can take this register and repeat it twice, and that's pretty cheap. So I talked to Matthias, who is working again on standard SIMD stuff. He says that in his view, an element repeating or elements coming in arbitrary order inside the SIMD register should be acceptable for you, for your predicate. So let's talk about the upsides. So the upside is again one argument type. It is nice to have just one argument type. And it is potentially fast, including stores. So this operation of extending the register and cutting it down is pretty cheap, and hopefully maybe even can be optimized away. Mm-hmm.
Why are the stores fast here but slow in the other solution?
Yeah, so the other solution says store, and here you go, a runtime value, store first 3 elements. So the way, the worst case scenario that's implemented is just literally memcpI. So you store it on the stack, and then you do two overlapping. That is quite expensive. Here, you have two registers. So let's say you want to, so this is just two overlapping stores. You need to select which one is, this is, if you have 7 bytes to write, this is two overlapping stores. There is no runtime value. No, that's not. Because you do this, and then another solution, you have to do the masking.
I see. This doesn't have the masking.
It doesn't have the masking, and it doesn't have to. Masking is not that bad, but like if you don't have the masking support, that's pretty bad. Okay, memcmp does this. It's a real memcmp that you use. Minuses. Again, like garbage values or repeated values, you have to accept that sometimes there's a value you didn't have in the input array. I don't believe there is existing implementation experience of a library that uses this as a SIMD algorithms interface. In if we use the previous one, I am really tempted to try to implement this, but I don't know what the implications are yet. For loads only, I believe that the aligned solution is still better. Like the doing the previous aligned address is like this one is better. I didn't measure it. Okay. So you were I asked already. Some like doesn't seem like people really on board with garbage values. I'm gonna make another case for it. I understand this not happening, but it's just better. But let's have a look. So this is what I'm going to do. I have two arrays, and I'm dividing A by B. All right, and like B might contain zeros, and if there are zeros, I want to skip some. So just basically those elements where B is 0, we don't do divisions. Let's look at the scalar code. You go from, we enforce it as the same size, and we just go. And if B is not 0, we do pushback A divided by B. Right. Perfectly fine. This is the same code vectorized with if. We don't have a pushback. There's no vectorized pushback. So we have to resize the output to the input size. Resize. Then we call, there is no filter view. So the best we can do is we have this algorithm called transform copy if. It combines the map and the filter and the store all together. We take the input range, we take the output. We accept, again, because we had to zip two iterators. This is zipped, we unpack them. And then look what I done. I divided A by B, and I return where B is not 0. So this is a division by 0. And if just says, this is fine. Like, if you divide by 0, we will not, like, you don't know that the value is in there, but it's going to be efficient. It's not going to crash on you. Okay, so what if we said there's a precondition in here? What's happening? So we write something like this. We do the test. Okay, so B is not 0. We replace all the elements in B with, I don't know, 1. And then we do the division. Now this is safe. But you introduce this if else. You introduce a branch. And this branch doesn't go away. So let me try to find it. Yeah, here it is. That's that if. The fundamental problem that you have in SIMD code that you don't have in scalar code is that ifs don't exist that much. Like there's a merge. You have to compute both sides and then merge them together. And because you have to compute both sides and merge them together, every time you have a precondition, you have to effectively check that precondition and make it sure that it doesn't trigger. So, which is still maybe fine to have preconditions that you check, but you eat the performance penalty for it. Okay. Unaligned access. I promised. Some people who really wanted it didn't come, which is hurting me. It's okay. Let's talk about alignment, because people keep saying SIMD and alignment and all that stuff. So how does it work? This is two cache lines. next to each other. So each cache line is like, let's say 64 bytes, right? If I load a register anywhere inside that cache line, this is just one load. It doesn't matter if the register is aligned or not, the pointer is aligned or not. It's a one load operation. If I cross the cache line boundary, it's going to be two loads that merge together. So this is just two loads in terms of cost. So if you align the pointers, let's say in my machine, this is again 32-byte registers. So if I go and iterate aligned, I always do two loads to load 64 to process 64 bytes. I do two loads and two stores. If I don't align, every other load will cross the cache line boundary, and this is going to be free loads to process 64 bytes, and also free stores. Does it make sense? Does it matter? Let's have a look. So this is a benchmark. It's a benchmark of a completely unrelated things that happened to show it, and so I'm using it here. We compare if transform in place with std transform. The operation that I'm using is just a plus. So I double every element by saying x plus x. So it is so happens, this benchmark, what's on x is completely unrelated. But what happens here is that every other time, malloc aligns to 16 bytes. Every other case here is either it's aligned to 16 bytes, and then either it's aligned to 32 bytes, then my loads are aligned, or it's aligned to 16 bytes, and then my loads are not aligned. So what I have here, and if just aligns the loads always, like it will do correcting. So when you get unaligned loads and unaligned stores on standard transform, we are about 40% faster. I don't know, as that was a bit much, like how does it, I can try to repeat some of it. No? Unaligned loads here cost you about 40% performance. How was that? There are a couple of, I showed this to Peter Cardes, and he had a couple of objections. One is that the data is an L1. This is micro benchmark. He says that it's likely if your data is not fitting into cache, you will not see such a big difference. Second objection is that operation is very cheap. We just do plus. So effectively are completely dominated by loads and stores. As long as you do something else more fancy, it will go away because you have time to do the store and the load. So this is his answer. On a practical note, we believe that you should align when it's cheap. So if it doesn't cost you anything, you should align your loads and stores. So what kind of, I will note here that I didn't say anything about special instructions. I didn't say anything about probably anything. It's just the way you write a loop. So what kind of library support do you need for it? If we went just all in on this, we have aligned pointers, aligned iterators, aligned everything. We keep track of it everywhere. We do everything we can to do. What do we get for it? Well, one we do is aligned load is safe tricks that we talked about and that we really cared about. We check if the input range is aligned, and if it is, we don't do any additional alignment. Right? We'll just say, oh, okay, it's already aligned. We remove a little bit of a tail handling code. And finally, there exist legacy instructions on x86 that requires that your pointer is aligned. So I talked to some Intel people, and they say those legacy instructions no longer matter. In fact, I believe Intel compiler will refuse to generate them. When I talked to Matthias Kratz, who's one of the standard SIMD people, he said he has a benchmark where legacy instructions still matter. In the standard, they have created the SIMD flag align. So the SIMD flag align is you basically pass it to a load, and then it will generate. So what do we get from it? So it tells us the load that the pointer is aligned to the appropriate size. What they get from it is they do generate the legacy instructions, And for certain things, like for example, if you know that you load the fixed sized range, it's a standard SIMD API. So when they know that there's at least 1 byte, in this case, they can use aligned load as safe trick. It's rare when that happens. I'm honestly not sure that it is worth it, especially to track it through all of the SIMD APIs, especially if you can get away with overlapping register handling. So I am not sure the SIMD flag align. The SIMD flag align doesn't bother me that much. Like exists, okay, but I'm not sure it's worth to continue to expand on that. So thanks to Peter Cardes, Ilya Albrecht, Mohamed Medjini, and Geoff Langdale for their input on the alignment stuff. I just asked people what's happening. Any questions about alignment stuff? Okay. I appreciate people who are still awake. That's really warmed my heart. This is really. Let's talk about the ranges. So what kind of views and ranges we can build to expand the algorithms? What in the world are we just talking about? Time and time again, people come with this idea that let's have a range of SIMD. We're going to take the input array and we're going to transform it into a range of SIMD registers somehow. And that, to the best of my knowledge, that doesn't really work. You can't pull it off. This is what I've been saying by saying this is not for each. Like you don't just iterate through a range of SIMD. You have tails, you have unrolling, you have all those things. So no. In fact, what we call range is like super close to what the standard calls range. The concepts are very similar. And the iterator is just the position inside your range. Okay. So can we do contiguous ranges? So could we just say any contiguous range is a valid SIMD range? Depends. In a few places, specifically, we said, I'm going to have a previous aligned address to the beginning of the array. I'm going to have the next aligned address to my current pointer. That might be outside of the array. Like you have an array with 3 elements, you say, give me the next aligned address, is going to be somewhere there. Not legal. Standard ranges, standard random access iterators do not support access outside of the array, but except for end. End is okay, everything else is not okay. So if your tail handling is masked loads, no. If you do something else for tail handling, maybe you still would like to compute the previous aligned, the next aligned. Maybe you can pull it off. So maybe, I don't know. If we want to need to represent those values, I think we could go with base plus offset model. So yes, there's this random access iterator somewhere, a contiguous range, standard contiguous range. And then we transform it into something that is base plus offset. If we have 2 types of iterators, we do the transformation from, like, let's say, vector iterators to pointers, do our operation, and then this is where we ended. This is the beginning of the vector. Let's just do the offsets. I don't know if that makes sense. Basically, we transform from standard iterators to internal iterators and then expose it. Contiguous. Sure. Is everything random access? Is everything we want to represent random access? And if everything is, however, there's one use case we cannot do, and that's scan. You can totally implement a scanning. You take a range and you scan is an inclusive scan, so partial sum of all the elements up to this point. Perfectly implementable with SIMD. Cannot make it into a view because it's not random access. So some other generators probably exist that follow the same model. So ideally, non-random access would be great. So what is our iterator model then? Is it okay if anybody have a question? That's cool. What do we have? So we can ask for a value type. This is the same as standard iterators value type. On top of just value type, we can ask for all of the types to consider. So this is the thing. Imagine if you converted from doubles to ints. Right? In this case, standard doesn't care. But in SIMD, what you would like to know is you would like to know that there, under the hood there is doubles, and so you don't want to use too many elements in the SIMD register, because otherwise you have to emulate the big one. So you need to know about all the types involved in order to choose the correct register size to use. Make sense? Okay. We have operator plus, minus, also comparisons, same as standard random access iterators. We have read and write. This is just operator star. We just didn't want to do proxy references. So in reality, that would be an operator star that returns you one value. Okay. And then we have load and store. Those can load you a SIMD register. You can load a SIMD register, you can store a SIMD register, and you can do any size of the SIMD register you want. There's also other things that we have that probably the standard shouldn't. It's all about alignment. Because we want to support alignment, we know how much the element, the iterator, how many elements the iterator is expecting into a SIMD register, so the cardinal. So I know that it's a double of 4 doubles, iterator of 4 doubles, or iterator of 8 doubles. And this is specifically to deal with alignment. You can change that, but then if you go up, you will drop the alignment. It stops being aligned. You can have like partially aligned queries. Is it unaligned iterator? I don't think the standard should do it. It's just what we did. So, given that, what kind of views can we do? Well, we can do conversions, which is useful. We can do zip. We can do map with a caveat that we don't like it. That's the way we do map. There's iota, so just numbers. There's a reverse view, and there's a backward view. What's the difference? So reverse view is the same as standard reverse. But what happens? Like, let's say you load 8 elements from the end. If you just load them from the end, you will not get them in the reverse order. So what reverse needs to do in order to match the behavior of standard reverse, it has to do the shuffle to move the elements around and backwards. That's expensive, so we have a backward view. I don't think it's very well defined, but it's super useful. So it goes into sort of the range as backward to front, but it doesn't shuffle the elements around. We don't have a filter view. I mentioned this a little bit, but generally speaking, you cannot, like, imagine you have a predicate and you need to combine the SIMD register out of it, but you don't know where the elements are. So how do you do that? So there are some schemas that people tried to do filter view in SIMD ranges stuff, but then it is just expression template. So it is just a tag type. Okay, this is my filter view. And the algorithm is supposed to figure out what to actually do with this filtering now. We believe in actual code, so we don't do those. So yeah, you have algorithms like transform, copy, if that mix filtering and transformations because no filter view. Map view exists, but it has, as I mentioned, it's not great. Specifically, this is a problem. So inside the map view, you need to have a predicate, an operation that returns you a new type. So in order to compute the value type, what's the value type of my operation, I need to apply the predicate. But value type is involved into how many elements should go into the register. If I produce a double, I should use my n will change. So this is the only place in Eve library where the operation is required to be a template that accepts scalar and SIMD values. Everything else, just always one register type. And people still complain about it. There was a proposal to do some sort of projections. So you would not have like a proper map view, but in algorithm, you would plug in something. I don't know how that would work. I'm thinking about it. Standard has projections. Standard ranges have projections. I don't know. Few more small things. Do you have questions about ranges? Okay. Sharing iteration logic. I mentioned that writing loops is very hard, but I also mentioned many times it's not just a for each. So you still want to share some way of writing loops. If we have a way, I don't like it, but it's there. So it's done through, instead of just having an algorithm, you have what we call an iteration. So it accepts some options, a range, and then a delegate. But it's a delegate. It's the difference between a delegate and a callback. It has a bunch of different operations. So okay, this is your tail, handle tail. This is your normal case. This is your unrolled case. You have to implement all of them. And they differ between different iterations. So what do we have? We'll have for each iteration. Yes, and that will have like 3 different callbacks for the tails, for the main one, for the unrolled one. We have one with fixed overflow, for example. In min element, you have an overflow. When your index overflows, you need to do something. So there's an iteration for that. With expensive optional part, so you have your normal loop, and then you have something expensive to sometimes do. So in search, for example, you want to jump, you do pre-checks, and then you jump sometimes to the expensive part, which does a full check. We have 2 stages. This is copy if, so it has like when you have to do unsafe stores and when you have to do safe stores. It would be cool if the standard provided something shared iteration logic. This is difficult to write. It's just difficult to do the index mask correctly. Performance portability.
So the previous slide was about I don't have to do the math to figure out when I'm entering the epilogue.
So
I just provide a callback and it will figure out when I'm in the epilogue.
Yeah. So basically exactly right. So if you open a standard algorithm, you will see a loop. In if, you will see a call to an iteration and a delegate. Because I would like to reuse that iteration pattern. Like, you know how people don't really use for each algorithm? Because for each algorithm is pretty useless. It's very easy to write without or transform algorithm. However, in SIMD, that loop just go through everything. It's difficult to write. So you have the things that writes the things that with few places you need to plug in. That we call iterations. I'm not sure that's the best approach, but this is what we have. Okay. Performance portability. I mentioned this a little bit. The C++ is interesting in a way. You write a code for a server. You write some code for a server. You take it on a phone. It will be pretty okay. It might not be perfectly tuned, but generally speaking, your loop will be an okay loop. Not the case with SIMD. You have those instructions are like on the modern machines, there are 1 instructions available. On old machine, different instructions available. And it's a very useful one. So we talked about compress. We talked about masked like loads and stores a little bit. There's also table lookup operations, super, super important, like things like P. And they are absolutely not portable. To the ridiculous degree, they're weird, they're not portable, they're super custom what's available. So what do we do about them? In if, we said we're not going to expose any of it. If you write if code and you run it on any platforms that we support, you will get a reasonable result. Even if you take as the oldest thing we have, and it will be okay. You will not get the 30 times slowdown compared to the scalar code. Basically. The standard said the other way, like the standard looks the other way. It said we don't care. It's a useful operation. We will give it to you. It's on you to know whether or not you can use it, and whether or not on the thing you deployed it to, it will be okay. Both approaches kind of not like I like Harvard better, but the standard people feel different. It's interesting conversation whether or not you can query it somehow. So can you ask, oh, this operation is good here or not good here? I don't know of any actual implementation of that.
Well, when you say compress is not exposed, you mean Eve compress internally will either use VP compress or the AVX2 algorithm.
In Eve, there is no function called compress. We have five different functions that have compress store, compress copy, compress stores something, right? All of those different functions that would use VP compress if it's available, or it would use some other stuff. But even VP compress is an instruction from IVX 512 that does it. Or BMI2 or whatever, right? It's a specific implementation. But that compress store operation, I know how to implement it because it's a more restricted operation that exposes less things. It does a more specific thing than just general compress. I can take it on a SSE2. I can take it on something very weak and write something that will work for you. Like literally, Eve remove on SSE2 for integers will be faster than scalar code by whatever. I don't remember how much, but it will be a win. And if you use standard compress, like the proposed one, or standard mask store, it will be, your SIMD code might be substantially slower than your scalar code. And it's completely on you to know whether or not you can do it.
So mask store would be like extract each index and like do
that's not the worst case scenario. The worst case scenario, if there exists an instruction on old x86 that does mask store, but it's absolutely ridiculously slow and unusable, so it should never be used. But yeah, you get the scalar code and it's going to be bad.
I see.
Well. Finally, controversies. Okay. So why not standard array? Why is any of this needed? Why can't we just use standard array? I like standard array. Standard array is great, and I have nothing against it. A few things here. One is that standard array it should be vectorized. Like, so if you write standard array and you write a loop on your standard arrays and it doesn't for some reason generate you good code gen, go complain to your compiler. In fact, if you look in something like standard unseek, internally, well, it's maybe not array, but it's like fixed loops with like 8 elements or something like that. Should vectorize fine. Main thing here is intent. So they do different things. One is a value type that stores a bunch of elements. It's like free integers. The other is the SIMD register that I would not recommend ask for size at all. Like it's a bit weird thing you do if you want the SIMD register of a specific size. There's a more practical thing. So size of 4 shorts, for example. Standard array makes perfect sense. That's 8. 8 bytes is 4 shorts. For, I don't know what specifically standard SIMD will ship, but for if you have a register with 4 shorts, that's going to be on x86, that's going to be 16 bytes. So twice as much. Why? Because the smallest register that's natively available is 16 bytes. That's going to be 16 bytes. Dynamic sizes that we don't support, but would be great. Like, what's array with unknown size? That's kind of weird. Some operations are also a bit sketchy, like element access. In array, element access is the most natural thing you do. You say element 3, element 5. I don't think I know a SIMD instruction set that would return you an element with a runtime index. So this is element access on the SIMD register would not be a super cheap operation. You have to store it on a stack and then access it. Just finally, the ABI thing. So again, I mentioned the under the hood one would be like whatever, some memory. The other would be a register. not sure how much this is a problem. So like 16 bytes, 8 bytes, different interpretation, differently passed through the stack. I'm not sure, like, what if you would give up and you say we just pass is the standard array and then the compiler unpacks it for us into what we actually want? It's probably usable. The calling functions with a SIMD as a parameter is not that common. It's okay. Matthias doesn't agree with me, and he thinks that this is important to get to insist on SIMD API. Anyway, those are the reasons why it's not standard array. Find regularity. It's like, how many people know this book? Do you know this book? Yay, one person. So this was a very big deal. Talked about this a little bit in the first part. Standard SIMD and if wide and all that, the operator equal returns you many booleans. The operator less returns you many booleans comparing by lane. There are many people who would say this is a very bad idea. Operator equal should return the bool. We all know what operator equal does. We know what operator less does. Right? So why have you not learned from val array? Like obviously everybody uses val arrays. That's the most successful type in the C++ standard. So why are you doing this again? Let's go somewhere. Let's first acknowledge that it could work. Can you build a system where the operator equals returns you a bool? Yes, it's a bit surprising in certain when you try to use it, but it is possible. When Eve first started, Joel used pairwise equal and had an operator equal return bool. When I first started messing around with this, I was like, all of the people are mental. Operator equal should return bool. I'm gonna return bool, right? Then you start looking a bit. First of all, std array, as we mentioned, is quite good. And every time I've seen that you want this to be bool, if you want the value type, you use standard array. SIMD is not standard array, it does different things. The goal of SIMD is a big goal of all of those operators and everything is for SIMD code and scalar code to look the same. So when you write your operation, you kind of don't think about it that much. Matthias calls this SIMD generic programming. Whatever. I looked through the Eve code base, looking for where do we return. So all of equal, this is how we would spell the return bool. The main usage is in tests. So in tests, in fact, when you say, okay, the expect, so whatever Eve's testing framework says for expectations, it will do the all for you automatically. There are some places where you check that to optimize things. So for example, sin would check, okay, is everything less than, is in minus pi over 4 to pi over 4? Let's then go to the shortcut version. But there you really want to say all, like it's helpful to say all. What about the operator less? What about the comparison? On top of, I have no use cases in Eve. I have one use case in production where I needed something like that. And to compare strings, I was comparing prefixes to strings. And so operator less would do lexicographical comparisons. That's a comparison. The problem is really tough to implement on top of everything else. It's not very well designed to do this lexicographic compare thing. So in production, I ended up not using SIMD and instead using integers. So I just, integers have the comparison that I want. So this is pretty useless, tough to implement. We talked about garbage values, right? Yes, people don't know wild about the idea. But still, you have some repeated values. So unclear what it actually would mean if you have some garbage values. Dynamic sizes, again, doesn't make a lot of sense. Like I'm comparing some number of elements and lexicographically less. The main argument at the end of everything is that we are not aware of any problematic use cases with doing like lane-wise operations. I'm not aware of anything where that would really be a problem. If there was use cases where this is really a problem and we're struggling, I would be with you saying that should return both. With you, meaning with people who think it should return both. So thanks to people who co-authored Eve, to Matthias Kretz for reviewing all the slides and providing his opinions, for all the people who do data par, like this was a lot of work, 10 years coming, and people sharing their research. A lot of the algorithms I didn't have to invent that many things, or Israel didn't have to invent that many things. We just look online and see what people wrote, the papers, the Stack Overflows, whatever, which is great. So some links, so the library and the slides, part 1, tinyurl.com, part 2. That's it. If any have questions, I'm happy to answer.
I would ask a question.
Okay.
So in the slide, masked loads tail handling, when we kind of load the data out of our arrays, like we start reading the elements before the array starts to be able to fit all the elements into the register. So what if we are on the page boundaries? So
this previous, I go to previous aligned address. Previous aligned address is always, page boundary is aligned to every register size possible. It's just 2 to aligned, so that never happens. Specifically, if you don't have, what can happen though, is if you have multiple parallel ranges, then so if you do zip, then you would align the first range and the second would end up somewhere. That one might cross the page long boundary. So in this case, we generate the instructions that would not cause a problem. So the masked load is okay with you crossing the page long boundary, or we do whatever it is we do for, we do memcmp. So we like that doesn't cross the page long boundary. It does make sense?
Yeah.
Oh, okay, cool. All right.
I was going to ask for division. If you just use the raw intrinsics, does it let you have some lanes that are
There is no division for integers. So there's only division. So the way integers are divided is you convert to double, and conversion from int to double is flawless. What's it called?
lossless?
Lossless. Yeah. You divide doubles, you get nonce, you convert back.
Nice.
Okay. Thanks for coming.